Right, and so let's talk about the 9.5 notes. This video is going to be as a part one and a part two. And so we are going to start with global climate change. All right, so the objective for this unit is, or this section is explain how changes in climate, both short and long term, impact ecosystems. Okay, and so we can look at climate change historically in terms of the um, geological history of the planet. And so let's start off by looking at one of the variances that occurs over time and how that impacts the climate and the change that we see in the climate. So the first thing that I want to talk about is eccentricity. And this happens approximately around every 100,000 years. Basically, the more eccentric that the orbit is of the Earth around the sun, the further it is away from the sun. And so this varies, and you can see in the graphic here over on the right-hand side of this slide how that changes. Again, that happens about every 100,000 years. It's just more elliptical or um, more like an more elliptical in the most extreme case of eccentricity there, and it's more circular, closer to being a perfect circle when it's obviously closer to the sun. All right, and then another thing that occurs in with the geology of the planet is a variance in obliquity. This happens approximately every 40,000 years. And you can see here that the tilt of the Earth is just a little bit different. It varies between 22.1 degrees and 24.5 degrees. And so what that does is it exposes more northern latitudes to a higher insolation. And we know higher insolation, that means lower temperatures, lower insolation, higher, more direct rays. And so that's what we're seeing again, approximately every 40,000 years. So this leads to a very predictable variation in climate. And the scientist that discovered that's name was Milankovitch. We call these the Milankovitch cycles. Again, you don't necessarily need to memorize these cycles specifically. These aren't words that you need to know, but you should know that it all has to do with these variations in how we're orbiting the sun and also in our tilt as we're orbiting the sun. And so we'll continue here. What you might say to yourself, well, how do we know that these temperature changes are happening? Well, scientists are actually able to go back and measure and estimate the historical temperature and CO2 levels using three different pieces of evidence. And so the first piece of evidence comes from foraminifera shells, which are protists that live in the ocean. When they die, their bodies build up in the sediment at the bottom of the ocean. And so different species of foraminifera, which is basically a plankton, or well, anyway, it's actually a zooplankton. Those different species have different temperature tolerances. And so we would expect to see different types of species in different temperatures. And so warmer would mean one type or one species would be dominant, whereas cooler would mean a different species would be dominant. And so that's what we're finding in the fossil records when we go back and look at these organisms. Or I'm sorry, at these geologic rock layers. And another thing that scientists are using as they are looking at ice cores, they can actually take an instrument, kind of like a soil probe, but they can drill that into the ground and pull out ice cores. And in those ice cores, they're actually able to investigate the air bubbles that are there. And those air bubbles contain ancient atmospheric gas, and they can measure the CO2 levels in those ice cores. So that's really cool and interesting research. And so from that, they're able then to determine how much CO2 was in the atmosphere at the time, which then tells us how warm the climate would be during those time frames. And then lastly, we can look at the radioactive isotopes of oxygen and the different concentrations in ancient ice. And so, if we have a lot more oxygen 18 isotope as compared to the standard O16, that means that we have higher temperatures occurring during that time. And so, we know what the half life of that radioactive isotope is. We can then measure that. I'm sorry, it's not radioactive. I don't know why I said that. I'm thinking of carbon. I apologize. So we just look at the different oxygen isotopes in those, and then those concentrations then can tell us how warm or how cool the average temperatures were. Okay, and so here we're looking at a graph of these cycles, Milankovitch cycles, and we can see that this is the carbon dioxide and the temperature of our planet looking over time. We notice here this really high shift. In 2014, the CO2 levels are like double what they normally are. And so this is telling us that this is man-made climate change as opposed to these standard Milankovitch cycles that we're used to seeing. Okay, so that's an interesting graph. The global ice ages that we notice here are followed by warmer periods. And like we said, these occur approximately every 100,000 years. Okay. All right. And so CO2 levels are strongly correlated with this temperature. We don't exactly know what's causing it, but we can see that obviously man has something to do with our current, massive doubling increase that we're seeing during this time frame. So. All right, and so what are the effects of climate change? Well, first of all, we know rising temperatures. Rising temperatures are going to lead to habitat and species loss, drought, soil desiccation, heat waves, increased precipitation, kind of depending on what the weather is doing during that time. And also, we know things like the weather patterns with the Southern Oscillation with ENSO or El Nino or La Nina can impact that as well. So that rising temperature, though, even if it's just 1 or 2 degrees Celsius, can cause major changes in those weather patterns. We also know now, after doing the last set of notes, the 9.4 notes, that we have rising sea levels, and that can be due to that glacial and continental sheet melting, as well as in combination with that thermal expansion that happens. We also have the melting of permafrost, which is that permanently frozen tundra soil that begins to thaw and release the stored methane and CO2 that is usually held underground in permafrost from the anaerobic decomposition that's happening in that soil. And so when that thaws, all of that methane and all of that CO2 throughout the Arctic regions are going to go up into the atmosphere, and that's a real problem as well. Here's just one example of kind of what that looks like when that, you can see this is a really like boggy, wet, lots of anaerobic decomposition happening here. When it doesn't stay frozen, all of that bacteria is going to, just start percolating and sending those gases into the atmosphere. Okay. And so we call this is an example of a positive feedback loop. As the temperature rises, the permafrost soil thaws, and we go further and further away from normal. Again, that's what a positive feedback loop is. And so that thawed soil then releases large amounts of methane and CO2, again, causing the temperature to rise. And this is just a loop that happens over and over again. Again, we're going further away from normal. That's why it's a positive feedback loop and not a negative feedback loop. And so, risks of global warming, let me take you back to that slide. I keep doing that where I hit the wrong button. Um, and so I like this graph because there are risks of global warming with just very small temperature changes. So so if we just look at how much the temperature has changed from 2006 to 2015 relative to pre-industrial levels, we can see that these things will start to happen just because of a 1.5 degrees Celsius change in temperature. So we don't even need, that much of a change for all of these things to happen. And then this is the different impacts, both economic, environmental, anthropogenic impacts that we're going to be seeing. And one thing that really scares me here are these crop yields are going to be impacted. So in other words, they're going to be decreasing because of the changes. And farmers are seeing that. And we know we're seeing extreme weather events, lots of different things are happening. All right, so what are the impacts on coastal communities? That's one thing we tend to think of because of that sea level rise. Well, we're going to see property loss, damage, potential relocation. We talked in the last section about refugees moving inland. They're going to be displaced from their homes along the coasts. Especially poor communities are going to be extremely impacted because they'll need to actually completely relocate. Seawalls and other buildings can be built higher. This really, though, just delays the flooding. Like, at what point does it cost so much to allow, to want to stay in a city like Miami? I know Venice, Italy is having a lot of problems with this. They have built seawalls. Miami's looking at having floating buildings. And all those things are great, but at what cost do you just say, all right, it's time then, to abandon the city? We'll see the loss of barrier islands. Islands that usually buffer coastal communities and ecosystems from both wind and waves could be lost as sea levels rise. And so that's a real problem because those barrier islands, like off the coast of the Carolinas, those really protect the mainland from erosion. And you can see here, here's more barrier islands, and now those are going to be gone completely. And there's a lot of homes on these barrier islands as well. I should note that as well. And so what are the impacts on atmospheric currents? Well, we'll have widening and weakening of Hadley cells. So that means that the temperature difference between the equator and the poles are going to actually start decreasing. The air is going to be ascending and expanding from the equator, and it's going to actually travel further north before it actually sinks. And so that's going to bring with it warmer temperatures and more precipitation. And that's going to happen all over the planet. And regions between 30 and 60 degrees latitude may experience even a drier climate, whereas things further south will experience a wetter climate. It's going to weaken and destabilize the jet stream. So as the Arctic warms faster than other areas of the Earth, that's going to cause those temperatures between the poles and the equator to the temperature differential to actually decrease. And when this happens, that will drive that polar jet stream, which means it's going to be a weaker jet stream. And it's going to allow a lot of cold Arctic air to move further south, which is what we've been experiencing in recent years, where we have these polar vortexes, as the weather people tell us on the news. These polar vortexes are staying in areas that they don't normally occupy. And so here is our FRQ for this unit. Explain how the data above support the hypothesis that a destabilized polar jet stream caused the cold spell seen in the Midwest in this diagram above. Okay, and that's it for 9.5 part 1. I'll come back in the next set of notes with 9.5 part 2, and I'll see you guys next time.